Okay, today we're going to talk about inverse functions. This is a follow-up of that last section 6.1 that talks about composition of functions. One of the first things I want to say about inverse function, I want you to keep in mind. To find the inverse, you swap the x and y. Now, if you'll keep that simple idea in mind, I think you'll find that doing this inverse is not nearly as bad as we think. But before we get there, we need to go to something else. Earlier in the course, we talked about the vertical line test. Okay, the vertical line test says if I got a graph, and let's draw the graph of this parabola right here, and I chop it up into vertical lines. If each of those vertical lines only hit the graph one time, then this thing is a function. It is a function. Now, in the idea of inverse functions, though, we've got to talk about a one-to-one function. Now, a one-to-one function must pass the horizontal line. The horizontal line test. And we can see, well, let's not clutter it up too bad. This is y is equal to x squared. That's the equation part. And it would fail the horizontal line test. So that means that this is not a one-to-one function. So in order to find the inverse of a function, it has to be one-to-one. Now I'm going to harp on this one a little bit later, and we're going to see how we can make this thing one-to-one by limiting my domain. And then we can also find now you got a problem like this. He's going to give you a graph. Let's plot -5, -5, -2, 0. 1, 2. Two, 4. Let's change it. I want it to come down some. Let's make this point right here. Let's make it 5, 1. Now, remember what I just got through saying. To find the inverse, you swap the x and y. Well, at this point right here, the x and y are both the same, so it makes no difference. Now, over here, this is -2, 0, so it becomes 0, -2. So 0, -2 is a point on my inverse. Now, 1, 2 becomes 2, 1. That's a point on my inverse. Now, 5, 1 becomes 1, 5. And that's not a good example of it. 5, 1 becomes 1, 5, and that would be way back up here. But the idea is still the same. To plot the inverse, you simply swap the x and the y value. And this thing is not drawn to scale because I have this 1, 2 over here. Doesn't pay to be sloppy all the time. But it works a whole lot better when you are working with equations. Another statement that I want you to put in your notes: the domain of the function is equal to the range of the inverse. The domain of the function equals range of the inverse. Okay, and I'm going to use that concept to talk about that thing that I said a while ago. If I tell you that f of x is equal to x squared, well, we already know that graph. We've done it many, many times, but let's put it over here and see what our problem is. The graph of x squared is our old friend, the parabola. But we've already shown that this thing fails the horizontal line test. But suppose that somewhere or another I could get rid of the left half of it. Then this half would pass the horizontal line test. Well, I can do that by limiting my domain. Suppose that I tell you that my domain is going to be x is greater than 0. So I'm going to start with x is 0 and then just keep using positive x's, positive x's. Now I do have a one-to-one correspondence, which is what I need. Now, suppose that I tell you that g of x is equal to the square root of x. Well, by the fact that this is a square root function, its domain has to be greater than or equal to 0. Now, the square root function, when we draw its graph, is going to look like this. Now, this point right here is going to be the 0.11. So this is the square root function. And then this is the x squared function. Now, let's do some numbers first. Let's do f of g of 9. Well, f of g of 9 will be the square root of 9, which is 3, and 3 squared comes out to be 9. And that's what we saw earlier in 6.1. When you put in 9, you get out 9. And I don't care which way you go, that's what it's going to do. Let's do f of g of 4. All right. Well, the square root of 4 is 2, but 2 squared is 4. So what if I just did the composition this way, f of g of x? Well, f of g of x, and g of x is the square root of x, but the square root of x squared comes out to be x. And that's the reason that this, when we put in 9, we get out 9. When we put in 4, we get out 4, because when we put in x, we get out x. And then that composition works both ways. Let's do g of f of x. Well, the g of anything is the square root of that thing, but f of x is x squared, and the square root of x squared is x. Now, what we just did is a very, very important concept. If two functions are inverse, the composition both ways will always come out to be x. Let me repeat that. That's important. When the functions are true inverses, the composition both ways will come out to be x. Now, there's an interesting little fact right here, because if I drew this line right here, this line would be the line of symmetry for this half of the parabola that we kept and for this part of the square root function that we have. In other words, this is the line of symmetry. Look at it, it just flips about that line. But that particular line happens to be the line y is equal to x. Okay, so suppose that I tell you that f of x is equal to x plus 4. And I tell you that g of x is equal to 2x minus 3. Okay. So it says that if I want to find the inverse of a function, I swap its x and y. So let's eliminate this one right now. Let's keep it simple to start with. So this says that y is equal to x plus 4. All right. So its inverse is going to be x is equal to y plus 4. So this says that x minus 4 is equal to y. And we're going to call that g of x. We're going to call that our inverse. So this is the inverse. And this is the function. Now, let's do f of g of x. F of anything is that thing plus 4. But g of x is x minus 4. Now you do the arithmetic. X minus 4 plus 4 comes out to be x. Let's do g of f of x. G of anything is that thing plus 4. G of x is that thing minus 4, excuse me. Now, but f of x is x plus 4. Same song and dance. Plus 4 minus 4 cancels out. So the composition both ways came out to be x. That means that we have found the true inverse. Now, an interesting thing is to look at it from a graph standpoint. The graph of x plus 4, when x is 0, y is 4, and when x is minus 4, y is 0. So that's the graph of the f of x function. Now, let's draw the g of x function when x is 0, y is minus 4. And when x is 0, y is minus 4. And when x is 4, y is 0. Look at it again. Visualize a little bit. If I drew that dotted line right down through here, and that's the graph y is equal to x, then these two lines, in fact, all three of these lines are parallel because all three of them have a slope of 1. But we have drawn the inverse. But the important thing is this. When I did the composition both ways, then it came out to be x. So I have found the inverse. Okay. Let's say that your function is 2x minus 4. And let's find the inverse. Now to find the inverse is very simple. You swap the x into y. So you simply say x is equal to 2y minus 4. Look what I did. I swapped the x and the y. F of x is understood to be y. Okay, so you take this thing, and this says that x plus 4 is 2y. X plus 4 divided by 2 is y. And we're going to call that g of x. Now watch this mess. Let's do f of g of x. F of anything is 2 times that thing minus 4. But g of x is x plus 4 divided by 2. This cancels, and you end up with x. Now let's do g of f of x. G of anything is that thing plus 4, the whole mess divided by 2. But f of x is 2x minus 4. So minus 4 plus 4 cancels out, and 2 divided by 2, and I come out with x. So we have found our true. Okay, suppose that I told that f of x is equal to x cubed minus 8. and we want to find the inverse. So I swap the x into y. So that says then x is y cubed minus 8. So x plus 8 is y cubed. So the cube root of x plus 8 is y. And we're calling that our g of x. That's our inverse. Now let's do f of g of x. F of anything is that thing cubed minus 8. But g of x is the cube root of x plus 8. But when you cube a cube root, it removes the radical. So you got x plus 8 minus 8. And x plus 8 minus 8 comes out to be x. Now let's do g of f of x. Well, g of anything is the cube root of that thing plus 8. But f of x is x cubed minus 8. Now, so this gives me the cube root of x cubed, but the cube root of x cubed is 8. It's foolproof. You swap the x into y, and then you solve for y in the second part of it, and that will always give you your inverse. One thing that I left off talking about this, and we did talk about the domain, the fact that we got to limit it. You got a homework problem that looks something like this. And they want to know what the domain of this thing is. Well, what you got to do is ask yourself, is there anything that will make that denominator 0? Well, we go back to section 1.2. We factor this mess, and it factors into 3 and 2. So x is 3 and x is 2. So the domain then, x can't be 3 because that made it 0, and x can't be 2 because that also made it. One other concept that you have to work with in this is dealing with those complex fractions. Now this is really just an algebra 2 problem. But let's take a look at it. This is what we call a complex fraction. And to deal with a complex fraction, we get rid of the denominators that's in the numerator and denominator. So I'm going to multiply the top by x squared, and I'm going to multiply the bottom by x squared. Now, when I do that, x squared times 1 over x gives me x. And then x squared times 1 gives me minus x squared. Down here, I have 1 minus x squared. Now, we do a little bit of fancy footwork. This thing, you factor out an x in the top, and you have 1 minus x left. In the bottom, that's a difference of 2 squares. So it's 1 plus x and 1 minus x. So this cancels out. So the final answer then is going to be x divided by 1 plus x. And I think you have that same problem in your homework. Good luck with section 6.2.